we want to find the derivative of the natural log of x. Y equals the natural log of x. Everybody's familiar with natural log and what it is, I hope. Right, it's just a logarithm with a base of e. Right, that's what natural log is. It's a log base e. So if we remember from what we were talking about the other day about like we were trying to rewrite, what were we trying to rewrite? We were trying to rewrite a to the x as something. So we rewrote it as e to the natural log of a to the x. Remember doing that? Hopefully. I hope. Well, we're going to do a similar thing here. We're going to raise both sides of this as powers of e. So this becomes e to the y equals e to the natural log of x. This is called exponentiating this equation, right? We're making it in the equation part exponents of a base e. And we could do it with a different base if we wanted to for a different context. But we're going to do it with e here. So that would give us e to the y equals e to the natural log of x, and e to the natural log of x ought to equal x, right? So would everybody agree that these two things here, y equals natural log of x and e to the y equals x, mean the same thing?
Yes.
Yeah.
All right, cool. So instead of taking the derivative of natural log of x, we're going to take the derivative of e to the y equals x. And since this is no longer written as y equals a function of x, we have to differentiate it implicitly. So we're going to take the derivative of both sides of it with respect to x. Good or no?
Good.
All right. So when we take the derivative of e to the y, well, y is a variable, right? It's e to the y. So what do we get if we take the derivative of that with respect to x? In order to do that, we need to take the derivative of it with respect to y, don't we? So what's the derivative of e to the y with respect to y?
Is it e to the y times dy dx?
Right, e to the y is if we take it with respect to y, and then since we're doing it with respect to x, we got to multiply by dy dx. Everybody okay with that left side? Right, remember that from yesterday, the derivative of an exponential function is just that exponential function. And on the right side, what do we get? Just 1, right? The derivative of x is 1. Which gives us what? Dy dx equals 1 over e to the y. Everybody okay with that?
Yes.
Yes.
All right. Now, I'm not okay with that. I'm okay with that whole process, but I'm not okay with this as an answer. Because we started off with something that was all in terms of x. So we'd like to finish with something that's all in terms of x. And I know we took the derivative of this, but really we started here. So how can we turn this e to the y back into something in terms of x?
Would it be 1 over x since e to the y is equal to x?
Exactly. E to the y is x, so we're just going to plug that in there and get that the derivative of natural log of x is just 1 over x. Okay. This is a rule that you're going to want to memorize. The derivative of natural log x is 1 over x. Good or no?
Good.
All right. What if instead of this just being an x in here, it was some other function inside the natural log? What rule would we have to apply to take the derivative?
Reciprocal rule?
No. If it was natural log of a function inside of here. So like natural log of x to the fifth, let's say. we'd have to rewrite it as natural log of u with u equal to x to the fifth. So we'd have to use the chain rule. So do you think we could replace the x with a u and use the chain rule?
Yeah.
Hopefully so. So if we want to take the derivative with respect to x of the natural log of a function, like 3x squared or something, then we're just going to do 1 over that function times the derivative of that function. So if we're looking for the derivative of natural log of 3x squared, that's natural log of u with u equal to 3x squared. And so our derivative of this ought to be 1 over u times the derivative of 3x squared, which is 6x, which would give us 6x over u, which would be what? Hopefully 2 over x.
Yes.
All right. Cool thing about logarithms of like nice little polynomials is they can be rewritten using log rules. Just for fun, let's do this another way. Couldn't I make this natural log of 3 plus the natural log of x squared using log rules? It's 3 times x squared, so we could separate that into 2 logarithms using a plus sign.
Yeah.
Yeah. And if we were trying to take the derivative of this, we could also move this exponent of 2 out to the front. Isn't that another log rule? And so now when we were to take the derivative, what's the derivative of natural log of 3? What's 3?
0.
It's 0, right? Because 3 is just a number, and the natural log of 3 is just a number. This is just a constant, so its derivative is 0, plus 2 times the derivative of natural log x, which is 1 over x. Just gives us 2 over x. So either way, we get the same answer. This is maybe a little bit more work, but kind of cool that it works out the same way. Let's look at another one. The natural log of 5 times the cosine of 2x. So using the chain rule, this is y equals natural log u with u equal to 5 cosine 2x. Good or no?
Good.
Okay. So the derivative dy du ought to be 1 over u. And the derivative du dx, well, how do I take the derivative of 5 cosine 2x?
Chain rule again?
Say that again?
Do you have to use the chain rule again?
Chain rule again, yep. This is 5 cosine v with v equal to 2x. So the derivative of 5 cosine v is negative 5 sine v times the derivative of v, which is 2. Everybody okay with both of those? So if we put that all together, negative 5 times 2 gives you a negative 10 sine of v, so sine of 2x, all over u, which was 5 cosine 2x. And what does that simplify to? Negative 10 over the 5 ought to give us a negative 2, and then sine 2x over cosine 2x is
Tangent 2x.
tangent 2x. Exactly. Good or not? Everyone okay with that?
Good.
All right. So what if instead of having natural log, I have a logarithm in a different base? log base a, right? Where a is just some positive number greater than 1, right? Some integer greater than 1. How many of you have never seen this change of base formula before? My guess is a lot of you, since that's what I discovered last quarter and during fourth period.
Yeah, I've never seen that.
All right, cool. So there's this thing, it's called the change of base formula. It lets you take a logarithm of any base. You can start with any base you want, and you can turn it into any other base that you want. So suppose I have log base 7 of 3. And you want that to be a logarithm in, anybody got a particular base they want that to be?
Natural log?
Okay, making me erase there, natural log. And so I can make it natural log of the original thing I was taking the logarithm of, divided by natural log of the original base. And it could be in any base that we want. So the natural log of 3 over the natural log of 7 should also be equivalent to log base 10. Normally we don't write the 10 if it's base 10. So log base 10 of 3 over log base 10 of 7. Or suppose I wanted it to be log base 2. That's the same as log base 2 of 3 over log base 2 of 7. Change it to log base 1000. It's the same. Log base 1000 of 3 over log base 1000 of 7. And this is the change of base formula for logarithms. Something they at least used to teach in pre-cal. I don't know if it was ever part of AIM 3, but I definitely taught it when I used to teach pre-cal and honors pre-cal. This is the change of base formula. You can turn from any logarithm, so for example, a logarithm in base A, to a natural log. Since we know how to take a derivative of a natural log, it seems like that's a good base to convert to. Yeah. Yeah. So log base a of x is equivalent to natural log of x over natural log of a. And I'm going to rewrite this as 1 over natural log of a times the natural log of x. And the reason I'm doing that is because what is 1 over the natural log of a in math terms? All right, let's start at the
Natural log of
beginning.
a to the negative 1.
It is, that's true. I'm thinking more simple than that. What's a?
A number.
A number, right? What's the natural log of a number?
A number.
A number. And what's 1 divided by a number?
A number.
Yeah, you guys are good at this. This is just a constant. So if I have a constant times a function, all I have to do is take that constant and multiply it by the derivative of that function. What's the derivative of natural log of x? It's 1 over x, right? And I need to multiply that by natural log of a. So the derivative of log base a of x is just 1 over x natural log a. Good or no?
Good.
Great. This is another rule that you're going to want to have memorized. So memorize that rule. All right, let's see if we can apply that into the chain rule. So the derivative of log base a of a function is 1 over the function times natural log a, and then times the derivative of the function. So let's do this with a simple one here. Log base 3 of x to the 5th. This is y equals log base 3 of u with u equal to x to the 5th. Good or no? breaking it up for the chain rule?
Looks good.
Okay. So the derivative of log base 3 of u ought to be 1 over u times the natural log of this base, so 3, times the derivative of u ought to be 5x to the 4th. So we end up with 5x to the 4th over x to the 5th ln 3. And we can cancel out a bunch of those x's to get 5 over x ln 3. Good or no?
Good.
Note that we could have, if we wanted, pulled that x to the 5th, that 5 exponent out in front. So we would have just had 5 log base 3 of x, and then we wouldn't even have had to use the chain rule, right? Log base 3 of x times a constant should just be that constant times the derivative of log base 3 of x, which would be over x ln 3. So we could have simplified it first. Works out nicely if it's just a single power in there, x to the 5th or x to the 7th or something. But either way you do it would be good. Any questions so far? This, I didn't want to be there. Let's see if we can figure out a way to find a derivative of x to the x. So we've had two different types of rules for things that were something to a power. One was the power rule for a variable to a numeric power. And then the other was the rules for exponential derivatives, which was a number to a variable power. But here we have a variable to a variable power. So this is a little bit different. We're going to have to use a logarithm to clean this up a little bit and make it workable. So what can a logarithm do for me? Any thoughts?
Could you take log base x of both sides?
So we can't take a log base x. We can't take a logarithm in a variable base. We have to pick a just a standard base to use, not a variable base. But you got the right idea. So let's take your idea of taking a logarithm of both sides and let's just do it with natural log. And I'm only choosing natural log, well, for a couple of reasons. One, because the derivatives of natural log are easier. And two, because natural log requires me to write less than writing out log, right? That requires me to write 3 letters, whereas natural log only requires me to write 2. So everybody agree that we could do this, take the natural log of both sides and it should still be equal?
Yeah.
All right, cool. So on the left-hand side, we just have natural log of y. Not really any way to simplify that, but could I rewrite natural log of x to the x power in some way now?
Can you rewrite it as like x times natural log of x?
Yes, definitely. Pull that power out to the front. Exactly. So now that we've done that, what can I do with both sides of this?
Differentiate implicitly.
Yep, differentiate implicitly. So what's the, I'll write this here in a different color. The derivative with respect to x of both sides of this. So on the left, what do we get?
One over y dy dx.
Perfect. 1 over y dy dx. And on the right-hand side, this is x times the natural log of x, which is going to require us to do what? Use what rule?
Product rule.
Product rule, good. So that'll be x, and then times the derivative of natural log of x, which is
1 over x.
1 over x, just from a few minutes ago, right? Plus derivative of x, which is 1 times natural log x. And so we end up with 1 over y dy dx equals, well, x times 1 over x is just 1, right? So 1 plus ln x. And we need to find dy dx, right? So dy dx ought to be y times 1 plus ln x. How do we feel about that answer?
Do we need to change the y?
Yes, we do. So we should feel not so great about this because we started with y equals something all in terms of x, and we ended up with a y in it. So let's take this x to the x that is equal to y and plug it in, giving us x to the x, so our original function, times 1 plus ln x. Good or no?
Good.
This is called logarithmic differentiation here. So rather than just taking the derivative of a logarithm, what we're doing is we are using the logarithm to turn our function into something that we can differentiate. Okay, logarithmic differentiation. Let's do this for another one. So anytime we have a function being raised to the power of another function or a variable to another variable, we're going to take the natural log of both sides. So that brings the x out in front. And then we can differentiate both sides with respect to x. So we're still going to get 1 over y dy dx. And on the right-hand side, this will again be the product rule. X times the derivative of natural log of sine x. Well, that's natural log u if u equal to sine x, right? That's a chain rule problem. So the derivative of natural log u is 1 over u, so 1 over sine x, times the derivative of sine, which should be cosine. Everybody good with the first part of the product rule there?
Yeah.
All right, and then derivative of x, 1 times natural log sine x. So what do we do with the 1 over y? Just like last time, we'll bring that 1 over y over as a y. So we got y times x cotangent x, if I simplify that, plus natural log sine x. Or when we replace the y with sine x to the x, we get sine x to the x, x cotangent x plus natural log sine x. Good or no? Any questions there? We're going to get rid of that last page and move on to what the other part of what we're going to do is. Which is finding the derivatives of inverse trig functions. So there's a whole lot going on here. All this stuff that I've written up here is stuff that you should have learned back in AIM 3 or in honors pre-cal or regular pre-cal or regular AIM 3 or whatever class you took last year. But basically what we've got is we've got the function sine x and inverse sine x. And these two functions are inverses of each other. Okay, so sine x and inverse sine x are inverses of each other on the interval for sine from negative pi over 2 to pi over 2. Okay, and on inverse sine from the interval from negative 1 to 1, meaning that we can't plug anything other than negative 1 to 1 into the inverse sine, right? Because whenever we take a sine value, the output that we get is always between negative 1 and 1. True?
Yeah.
Everybody is hopefully familiar with inverse sine, right? You plug in a number between negative 1 and 1, and the output of inverse sine is just the angle, right? And that angle is always between negative pi over 2 and pi over 2. Okay. So if all of this is true, and if sine x and inverse sine of x are inverses of each other, then I should be able to say that these two statements, these two equations are equivalent equations. Y equals the inverse sine of x. If I were to take the sine of both sides of this, then I should end up with sine of y equals x. Right? Because the sine of the inverse sine should just come out to be my original angle. Right? That's how inverse sine works. True? We're all moderately familiar with that at least? Yeah or no?
Yeah.
Okay. So since we don't know how to take the derivative of the inverse sine of x, but we do know how to take the derivative of the sine of y, we're going to, instead of using this equation to find its derivative, we're going to use this equation to find its derivative. So I'm going to give us a new page here. So we got some room. We got x equals sine of y. And how do we take the derivative of that to find dy dx?
Do we use implicit differentiation?
Yes, we most definitely do. So we got the derivative with respect to x of x and the derivative with respect to x of sine y. And so on the left-hand side, that's just 1, right? And on the right-hand side, when we take the derivative of sine y with respect to x, what do we get?
Cosine y dy dx.
Perfect. Cosine y dy dx. So what does dy dx equal? It equals 1 over cosine y, right? But what's the problem with getting 1 over cosine y?
It's in terms of y.
Exactly. It's in terms of y, which is a problem. So how are we going to turn cosine y in terms of x?
Inverse sine on that red equation.
Say that again?
Inverse sine on the red equation.
From the invert, this one right here you're talking about?
Yeah.
Okay. I'm not sure exactly what you mean by that. You mean to take the inverse sine of it?
On both sides.
Oh, I see. So you want to get y equals the inverse sine of x and get the cosine of the inverse sine of x?
I think so.
Okay, so you want to get y equals inverse sine of x, which is the equation we had here to begin with, right? And plug it in. Okay, that will definitely work. But This is still a little bit of a pain to evaluate most of the time. And there's actually a much nicer way to get this written. So there's nothing wrong with doing it this way other than this is a pain. And there's a really clean way to write it. And something that you're going to want to get used to is whenever you have to deal with these angles, put them on a right triangle, right? So what does x equals sine y mean on a right triangle? It means that the angle is y, and that the sine, which is opposite over hypotenuse of that, is x, right? Or just x over 1. Would you guys agree with that?
Yeah.
Right, if I said like sine theta equals 7/2, right? That wouldn't make any sense. Sine theta equals 2/7. You put a theta here and a 2 and a 7, right? And you could use the Pythagorean theorem to find this last side. 1 squared ought to be x squared plus, I don't know if we call that a, x squared plus a squared. And what would a then equal?
The square root of 1 squared minus x squared.
Right, square root of 1 squared minus x squared, or just 1 minus x squared. And now, just by using this triangle, we should be able to figure out what the cosine of y is. Cosine is adjacent over hypotenuse, right? So cosine y is root 1 minus x squared over 1, or just root 1 minus x squared. So this becomes 1 over root 1 minus x squared. And that's a little easier generally, especially for just regular values of x to evaluate than the cosine of the inverse sine of x. So this right here is the derivative of the inverse sine of x. And you're going to want to memorize that. Good or no? Any questions on that? Do you think we could apply the chain rule to this if instead of having inverse sine of x, I had like inverse sine of a function? Hopefully so. So inverse sine of u, let's suppose it was like inverse sine of x squared. That we wanted to take a derivative of. That would be y equals the inverse sine of u, with u equal to x squared. And so we would just go through and we would use this formula, 1 over root 1 minus u squared times the derivative of u, which is 2x. And we get something like this, 2x over the square root of 1 minus x squared, or x to the 4th. Good or no?
Good.
Cool. All right. Now there are 5 other inverse trig functions. All 5 of them can be proven, the derivatives can be proven in basically the exact same way. So I'm not going to go through and do all of those. Here are all of the derivatives of the 6 inverse trig functions. You're going to want to know these. And these are the chain rule applications of each of them. So if it's inverse sine of a function, it's 1 over root 1 minus the function squared times the derivative of the function. Notice that inverse sine and inverse cosine are almost exactly the same. Right? The only difference between them is a negative sign. And for tangent, 1 over 1 plus u squared, and cotangent, notice that the only difference between them is a negative sign. And the same for secant and cosecant. So really, if you can memorize sine, tangent, and secant, the co-functions of each of those, just throw a negative in front of them. Should be a little bit easier to memorize. Good or no?
Good.
All right. And there is a document already up in the Google Drive that has not just these, but all of the derivative formulas that we've learned so far in it. It's in the other documents folder, so that'll help you with memorizing them all. All right, let's do a couple of these. Let's at least do the first 3 here before we get out of here. That way we'll have done one with sine, one with tangent, and one with secant, which are basically the same as doing the co-functions. Just put a negative in front. So we'll start with inverse sine of root x. So y equals the inverse sine of root x is y equals the inverse sine of u with u equal to root x. Everybody good with starting it off that way?
Yes.
All right, so this becomes the inverse sine of u's derivative is 1 over root 1 minus u squared. And then we have to multiply by the derivative of root x, which is 1 over 2 root x. So we got 1 over the square root of 1 minus root x squared times 1 over 2 root x. And that ought to simplify to 1 over 2 root x and root 1 minus x if you simplify what's inside that radical. Everybody good with that or no? Everyone's good?
Yes.
All right, let's do the next one. So inverse tangent of x squared. This is the inverse tangent of u with u equal to x squared. So the derivative of inverse tangent of u is 1 over 1 plus u squared, and I'm just going to plug in the u as x squared right off the bat. And then we got to multiply that by the derivative of u, which is 2x, and we end up with 2x over 1 plus x to the 4th. Good or no?
Good.
All right. And one more. I think that last one on that page was the inverse secant of root x squared minus 1. So this is the inverse secant of u with u equal to root x squared minus 1. And inverse secant of u should be 1 over the absolute value of u times the square root of u squared minus 1. And then we have to multiply that by the derivative of u, which that's u equals root v, with v equal to x squared minus 1. So that ought to be 1 over 2 root v, and then times the derivative of v. So chain rule within the chain rule. Good or no? Everybody good with getting to there? And then we'll simplify real quick and be done for the next 9 days. So hang on for like 1 more minute. 2's will cancel. a square root is always positive, right? Or 0, in which case the absolute value doesn't affect it in any way. So really what I've got is the square root of x squared minus 1 times the square root of x squared minus 1, which is just x squared minus 1. And then this, if I square the square root of x squared minus 1, I just get x squared minus 1, minus another 1 is x squared minus 2. Any questions or issues with that one? All right, that's it till after Thanksgiving.